All right. Hello, everyone. Good evening from West Virginia. This is CR Bhatta again. Welcome to another episode of ANPA Colloquium series. We have two presentations today, so please be with us. Today, we have two very energetic young physicists working on two separate burning topics in the field of physics or physical sciences. So I would like to welcome our first speaker, Mr. Vishnu Pandey. Mr. Pandey did his bachelor's from Tribhuvan University, Siddhanath Science Campus, Mahendranagar, Kanchanpur in 2005. Then he did his master's in physics from Central Department of Physics, TU in 2008. And currently, Mr. Pandey is a PhD student with physics major at Hampton University, Virginia, since fall 2014. His research area is experimental nuclear physics, and currently he is doing his research at Jefferson Lab, Virginia. And his today's talks topic is title is a possible observation of lambda NN continuum structure and a bound sigma NN state using the E prime K plus reaction. So let's welcome him. And Mr. Pandey, floor is yours now. Go ahead, please.
Okay, thanks. Good evening, all, and thanks to ANPA for this opportunity. I'm Vishnu Pandey from Hampton University, and I'm working in the experimental nuclear physics in collaboration with Jefferson Lab, which is located in Newport News, Virginia. And in this talk, I'm going to discuss the analysis result of latest hypernuclear physics here in experimental hall a Jefferson Lab. Okay, so let's introduce the hyperons first. Well, according to the standard model of particle physics, baryons are the three quark structure. The common examples of baryons are proton and a neutron. The proton is shown here in the first figure. It consists of three quarks, U, U, and D. These three quarks are held together by strong gluonic force of attraction, and a neutron also has three quark structure, U, D, and D. Okay, so what is a hyperon then? So if at least one of the quark, either of the U quark or D quark, is replaced by a strange quark, the baryon is then called hyperon. So the hyperons are the baryons with at least one of the strange quark. These hyperons are represented by, this is conventional representation, by uppercase Y. And one major characteristics of these hyperon is their lifetime, which is much smaller than in comparison to proton and a neutron. For example, the lambda hyperon has lifetime is only about 260 picosecond. And up to now, four different families of hyperon has been discovered: the lambda hyperon, sigma hyperon, xi hyperon, and omega. So this is about hyperon. So what is a hypernucleus? Well, as you know, the nucleus means the combination of protons and neutrons. If at least one of the nucleon in the nucleus is a hyperon, the nucleus is then called hypernucleus. Okay, so how to produce the hyperons? Well, in Jefferson lab, we used a high energy electron beam to produce the hyperons. In my experiment, we used 4.326 GeV electron beam. So this high energy electron beam was allowed to incident on a target, let's say a hydrogen target, which is a proton. Since proton is a charged particle and the beam electron is also a charged particle, as you know, the uh, two charged particles interact by exchanging a virtual photon. So if the energy of the virtual photon is sufficient enough, this break these gluons, and this actually can create quark anti-quark pair S bar. Immediately U, D and S quark combine together, they form a lambda particle, and the remaining part I denoted by green color U and S bar. They combined together to form a meson, which is a K plus ion. Okay, the electron has long lifetime, so the electron can be measured by a physical detector. The kaon can also be measured by a physical detector. However, as we discussed, the lifetime of lambda particle is very small, so it cannot be measured by a physical detector. Also, it is a charged particle, sorry, chargeless particle. Well, so how to measure the lambda? So to measure the lambda, so the electron is reconstructed back to the target. The measured K plus ion is also reconstructed back to the target. Actually, we need the information at the reaction vertex, and then by using the energy and momentum conservation principle, the missing mass of the lambda can be measured. Okay, the once the lambda is produced in the nucleus, it may stick to the nucleons and form a hypernucleus, or if the momentum of the produced lambda particle is higher than the Fermi momentum or the threshold momentum, it can actually skip the nucleus. Okay, well, since the lifetime of the hyperons is very small, therefore the hyperon nucleon interaction and the hyperon interactions are very difficult to produce as compared to nucleon nucleon interaction. Therefore, very limited data exists for hyperon-nucleon interaction. For example, in case of lambda proton interaction, the data exists. I mean, the experimental data exists. The data was taken more than 50 years ago with a bubble chamber experiment, but the data itself is poor with low statistics and high error bar, and beyond this point no experimental data exists. The lambda newton interaction is the missing piece, meaning no experimental data exists for lambda newton interaction. Therefore, the lambda newton interaction is considered as identical with the lambda proton interaction, and in reality this may not be true. And here is the puzzle about charge symmetry breaking. I have a helium atom, a system of two protons and one neutron, and there is a mirror image of helium atom, a system of one proton and two neutrons. Now, if you measure the ground state, the binding energy difference between these two mirror nuclei after subtracting the Coulomb interaction, all you found 80 keV. I mean the binding energy difference between these two nuclei after subtracting the Coulomb interaction, the residue is only 80 keV. This is a small value and can be explained by theories. However, if I include a lambda here and one lambda here, now it becomes A equal to 4 isospin mirror pair of hypernuclei. So for the ground state, the binding energy difference is more than 270 keV, several times larger than what we found in A equal to 3 case. So the question is, if the lambda proton and the lambda neutron interactions are identical, where does this significant charge symmetry breaking comes from? Okay, so only the experimental data on the lambda neutron interaction can explain this situation, and this is the result of HYPE experiment at GSI. It is in Germany. So in this experiment, they used heavy relativistic ion collision method. They actually bombarded lithium into carbon graphite to produce the hypertritone, and the experiment was measuring the lifetime of the hypertritone. Then by reconstructing the missing mass, they found a point with an unexplainable peak, and they claimed it to be a bound state. A neutral system, three neutral particles are claimed to be a bound state. This was quite exciting result, and this excited a lot of theorists. And the theoretical calculation ruled out a lambda Newton bound system. However, later theories contradict this phenomena. I mean, the later theories, they did not agree the lambda Newton bound system. These theoretical studies indicated that the lambda Newton resonance may likely exist, and by measuring the binding energy and the natural width of such a state, it is possible to extract the lambda Newton interaction. To make a long story short, this experiment indicated the existence of either the bound state or a resonance state. Therefore, our experimental Hall A with tritium target aimed to search for the lambda Newton resonance or the bound state as indicated by the hype experiment. The experiment aimed to provide the experimental data on the lambda Newton interaction and to solve the existing puzzle of charge symmetry breaking for A equal to 4 isospin mirror pair of hypernuclei. However, the system was not ideal for this experiment. Well, the electron arm was at very large angle. This was the lowest possible physical angle for the current HRS system. However, this large angle produces very large value of Q square, about zero point 0.5 GeV over C square. As you know, the Q square is inversely proportional to the virtual photon flux factor, which results the very low value of production yield. The path length for the hadron arm was too long, and the hadron arm was detecting the K plus ions, and most of the K plus ions got decayed before they actually travel this long distance to the detector system, and this limits the K plus ion survival rate by about 10%. To provide sufficient momentum to K plus ion, the three momentum transfer is too high, about 400 MeV over C, way above the threshold Fermi momentum, which is about 270 MeV over C. So this makes our cross section even smaller than what we expected. And there is another thing, which is the K plus ion efficiency of the aerosol detector, which was very low. Okay, this is the experimental hall. This is the largest hall among the four experimental halls in Jefferson Lab. Its diameter is about 53 meter. This is underground, and its height is about 17 meter. Well, this this arrow shows the electron beam direction. This is a target. The high energy electron beam hits the target. Scattered electrons are transported to the left arm or electron arm, and there is electromagnetic interaction as well as the weak interaction takes place, and a lot of hadrons are produced, and these hadrons are transported. They have to travel this long path length to the right arm detector system. These two are the spectrometers, high you know left spectrometer and the right spectrometer. They contains mainly three parts: the magnetic particle transport system, which is made from the combination of dipole and dipole magnets. These are superconducting magnets, and some of them are big magnets. For example, the dipole magnet is more than 6 meter long. Okay, and the second part of this HRS is the detector hut. These each arm is provided their separate detector hut. All of the detectors are installed in the detector hut. This is actually like a two-story building. In the downstairs, all of the detectors are installed, and in the upstairs, the electronics are stored. Okay, the third part of the HRS system is the data acquisition system, which is a software part. This is the detectors we have used in this experiment. The particle reaction takes place at this point, and this distance is more than 20 meter. The first detector is the vertical depth chambers U and B. These are represented by U and B. These vertical depth chambers are used to track the particles, to find the precise position of particle, position and direction in the focal plane. And the next detector is S0, which is a scintillator plane. There is another scintillator plane. The scintillator plane consists of the photomultiplier tube. Any charged particle passing through this scintillator plane, that create a signal. When the same charge particle passes through another scintillator plane, it also creates a signal here. So we know the time of this scintillator plane, we know the time of this scintillator plane, and there is a fixed distance between these two particles, so that we can calculate the velocity of the charged particle. In between these two scintillator plane, there is a gas Cherenkov detector. It is a rectangular tank filled with carbon dioxide gas, CO2 gas. Electron passing through this Cherenkov detector can produce a signal, but none of the other higher particle can produce the signal. Therefore, it is considered a powerful tool to separate electron from the rest of the particle. These are also the particle identification detector. They separate particles on the basis of energy deposited to these detectors. These are called pre-shower and shower. In the right arm also we have identical configuration of detectors, except in the right arm we installed two aerosol detector A1 and A2, because the gas Cherenkov detector cannot separate the Kepler's ions. Okay, so this is our target system. For the production target, we used tritium gas. The gas was contained in the aluminum cylinder. This is aluminum cylinder. This is a gas region, and this is aluminum entrance, beam entrance, aluminum window. It has a beam exit aluminum window. So when beam enters to the aluminum cell, beam has to interact first with the aluminum material, and then it has to interact with the gas region, and finally when the beam exit to the cell, it has also interact with the aluminum cell. Okay, so this is the reconstructed z vertex. The first peak represent the interaction of electron beam with the aluminum entrance window, and this is the aluminum exit window. This region is the interaction with the gas. And for the physics analysis, we assumed, or we considered, from minus 10 centimeter to 10 centimeter. Well, after the calibration, the Z vertex resolution of about 4.5 millimeter is achieved, which is quite acceptable to our experimental requirements. And to calibrate the angles, or to measure the value of angle precisely, we took some data with a sheep slit plate. This is a tungsten sheep slit plate, and holes are drilled in the vertical and horizontal direction. The hole size is about, the diameter of each hole is about 4 millimeter. It has two bigger holes, one at the center, and the bigger hole is diameter about 6 millimeter. Well, only those charged particle can pass through these the sheep slit plate, whose track passes through the center of these holes. All of the other particle will be blocked by sheep slit. Okay, let us discuss a little bit more on that. So this is my target, which is 25 centimeter long. At this point we install the sheep slit, and this is a magnetic transport system, and here is the focal plane, or vertical depth chamber. So particle is detected at this point, but we need the precise knowledge of particle at the target. Therefore the information obtained at the focal plane is converged into the target by using the backward transfer matrices. And these are the reconstructed angles. The first one is the left arm. Each spot represents one sheep slit hole. It has two big holes. there is one big hole and there is another big hole. These red crosses represent the nominal value of the holes because each hole has a defined value of angle. It looks like each hole is landed at its ideal value, which verifies the quality of our calibration. This is the right arm. In the left arm, the holes are much clear, but in the right arm, there is a lot of background. This is because in the right arm, we were measuring the hadrons. So, because of the electromagnetic as well as the weak interaction, a lot of hadrons are produced. They are punching through the sheep slit, producing the secondary background. Also, in the right arm, our particle identification detector, the aerosol detectors are not 100% efficient. Therefore, there is a lot of background. Okay, so this is the coincidence time spectrum. That means we measured one electron in the left arm that has a coincidental K plus ion in the right arm. These are the coincidental pions and protons. These should not be here, but our detectors are not 100% efficient. Therefore, we cannot reject 100% pions. But all we care about the K plus ion, which has resolution about 370 picosecond, and kaons are cleanly separated from the pions and protons. This is our kinematic space. The momentum calibration is two-dimensional correlation, and we have only three data points to calibrate our momentum matrices. The one is the blue line, which is lambda from hydrogen data, hydrogen kinematics. There is another blue line, and there is a pink line. In between these two blue lines, there's a big kinematic space, and this is our experimentally interested region. There's a big kinematic gap, therefore the optics quality may not be uniform around our interested region. Therefore, we involved aluminum data in the matrix tune, which has negligible angular dependence. So to involve the aluminum data in the matrix tune, we selected the beam entrance aluminum window and the beam exit aluminum window. We combined it and we plotted the 27 magnesium lambda hypernuclei. The spectrum is before we involve aluminum in the matrix tune. First of all, we did a peak search test tune to find a single particle, a single real state, and after we found it, we involve aluminum in the matrix tune. First of all, we have only one peak. The region was gradually becoming more and more uniform, and more peaks were shows up. And finally, we found four nice peaks. One of them is bound by 3.3 MeV, and some of them are at the higher excitation. I hope this might be a separate publication. Well, after the calibration, this is the lambda and the sigma zero missing mass. This is hydrogen data, hydrogen kinematics. Lambda missing mass is landed right at its nominal value, which is 1115.68 MeV. But sigma is slightly only 20 keV away from its nominal, which is very small, negligibly small amount. This might be because of the statistics, low statistics. And here is another lambda from a different kinematics. This also landed at its nominal value. And after optimization, we achieved the required resolution, which is less than 1.5 MeV in sigma. In the correlation line, these two lines are very close to each other. Therefore, their resolution is very much close than this one. Okay. Some of the tritium experiments reported that there is a hydrogen contamination in the tritium gas. That means in the tritium target, some of the hydrogen is present. Therefore, we did the same test. Actually, I plotted the tritium data by considering the hydrogen as a target and lambda as a threshold mass, and we found a nice peak at the right above the threshold region, and this verifies the presence of hydrogen in the tritium gas. This is the result of our analysis. The green crosses represent the accidental background. This is obtained by analyzing the 38 accidental peaks and then scaled down by 38 to reduce the statistical uncertainty. And right above this accidental background shape is dominated by the lambda and sigma quasi-free event. The lambda quasi-free start right above threshold or right above zero. It goes all the way to this point, and above this point we assumed a pre-lambda from hydrogen contamination, and the lambda quasi-free line continues to this dotted red line. Above this dotted red line there is a solid red line which is a sigma quasi-free, the sigma quasi-free, and we plotted two vertical dotted lines here. These are the threshold masses of sigma hypernuclei. The first one is the lowest threshold, and the second one is the highest threshold. There is a peak, I mean this peak or this peak, which is the dotted blue line, blue Gaussian. This is the pre lambda from hydrogen contamination, and this is our interested region. The peak, I mean the small peak right above the zero, it was expected. The fitting shows the mean of the peak is about 0 MeV with a peak width of about 0.81 MeV in sigma. It has high errors. This is because the statistics is very small. We noticed another enhancement at the higher excitation, about 8.5 MeV with a resolution of about 1 MeV in sigma. The peak at such higher excitation was not expected, therefore we don't know its origin. Well, because of the low statistics, none of the peak can be solidly confirmed. Okay, the result I'm going to present here is very much interesting. I plotted the same mass spectroscopy spectrum with higher bins to reduce the statistical uncertainty, and the small peaks are still there, and the hydrogen contamination is also there. But we noticed another enhancement uh, at the sigma threshold region. This was actually predicted long ago, but nobody could found it. Therefore, the peak is not a surprising peak, and it can be explained. Okay, to conclude, it is possible to study the three-body final state lambda neutron-neutron interaction or sigma nucleon-nucleon interaction by using our Hall A system. However, for the higher statistics, the system need to be optimized. From this experiment, two lambda resonance states and one sigma bound state were observed. However, to make a definite identification of the observed states, higher statistics are required. A simulation predicted the intrinsic missing mass resolution of A equal to 3 resonance to be about 0.66 MeV with a natural width of about 0.55 MeV. However, due to the low statistics, the precision does not permit a sufficient constraint in determination of the unknown lambda neutron interaction. This is experimental Hall A. The beam is coming this way. There is our target chamber. This is probably the first quadrupole, second quadrupole. There is a dipole. There is a detector hut. This is left arm only. Okay, thank you.
Uh, Thank you, Mr. Pandey, for your nice presentation. So we will take a few questions for Mr. Pandey. So I would like to go first with I would like to take questions from chat box first. Then you guys can just unmute your microphone and ask your question if you have. Okay. First question is from Anil Panta, and he's asking, what do you mean by optimizing the system for higher statistics?
What do I mean by optimizing the system for? Okay, well, thank you for the question. Okay, so we took a lot of data to for this experiment. Let me go back to a couple of more slides. Maybe here. So optimizing the system meaning the lowest possible angle for the current HRS configuration is 13.2 degree, right? So this gives a very low value of cross section yield. If we change the HRS, actually the right arm, into the HKS detector, we already have it, but it takes a long time, more than 6 months to install the system. This angle can be reduced by a factor of 2. We can do it 6.5 degree, so we have high value of production yield. And the path length for current head is 26 meter, but this can be reduced to 11 meter. Right now the Kepler only 10% K can reach our detector system, but if this reduced to 11 meter or 12 meter, at least 40% of our K can reach the detector, right? There is another thing, because the 10%, only 10, most of the kaons are decaying in the in traveling the long path length. Therefore we provide high momentum. So if the path length is smaller, we can still reduce this momentum, so that at this time, once lambda is produced in the nucleus, it has a higher probability of escaping the nucleus without sticking to the nucleons. So this can be managed. Another thing is the kaon detector in the right arm. So the available aerosol detector, if you send 100 kaons, they can only measure 50 of the kaons. 50 of them cannot be measured because their efficiency is very low. So if we have 100% efficient PID detector, we can have 100 kaons, right? By this way we can increase our production yield. I think I answered your question.
Thank you, Mr. Pandey. We have like few more questions. If you think you can give, they have like short answers, please try to attempt now. Otherwise, we might do like you can reply on chat or we can discuss later because we have another presentation as well. So if you want to answer quickly, I would like to take question from Bhavin Tital. He's asking electron beam energy used in this experiment is 4.3 GeV. Was this experiment done before CEBAF 12 GeV upgrade? I hope you will understand this term from Bhavin Dital.
The experiment is the first, never done all over the world. So this is first time we attempted this experiment. But CBAF can have 12 up to 12 GeV electron beam.
Okay, thank you. We have another question from Ashok Timsina. He's asking, is there any way for improving higher statistics?
We already explained these, so this is the way to improve the statistics. The here the same page.
Okay. We have another question from Ishwari Parajuli, and he's asking, what is the magnetic field value produced by Qqdq?
Oh, I'm sorry, I do not know the value of the magnetic field. This is, I don't know. We don't actually do, actually the technician people measure it and they actually publish a report for after every experiment. But the purpose of quadrupole is focusing the particle, and purpose of this dipole is bending the charged particle to these detectors. I don't know the exact value of magnetic field. Maybe I have to go to their report.
Okay. Thank you for your presentation. And everyone, if you have any question, we will discuss later after our second presentation, or at the same time, you can put your question in chat box so that Mr. Pandey can answer there. So we will go to our next presentation. Ghanshyam, are you ready? So, would you like to share your screen?
Yes, I'm
Chandra,
ready.
can you stop the recording and then restart, okay?